This is our fourth video on laws of thermodynamics, and in this video we will continue practicing PV diagrams and efficiency and learn to understand how to use the formulas that we saw in the previous videos. So it's another video with lots of practice. So in this video they say a Carnot engine using a monatomic ideal gas as a working substance operates between two reservoirs held at 300 and 200 Kelvin. So there's two temperatures, T1 and T2. So the bottom one is T1 and the top one is T2. So between K and L I have isothermal process, and between N and M I have isothermal process. And starting at point K with a pressure of 310 to the 5th newtons per meter squared or Pascal, the volume is 210 to negative 3 meter cubic, and absolute pressure, and absolute temperature 300 Kelvin. The gas expands isothermally to point L. So you have K, L, M, and N, where the volume expands to 410 to negative 3 meter cubic. 500 joules of heat energy is absorbed by the gas in this process. So you have 500 joules of heat added between K and L. How many moles of gas are present? So for A, I can use PV is equal to nRT. So PV is equal to nRT, and I'm using for the point K. So the pressure at P is 310 to the 5th. The volume at K is 210 to the negative 3. And the number of moles we're looking for, R is the ideal gas constant. So that is 8.3 gas constant. And then the temperature at K is 300. So from here I can tell that N is equal to 0.24 mole. In the next question they ask, find the work done on the gas during K to L process, and that is isothermal process. So we can say that the change of the internal energy of the gas is equal to 0. And because the change of the energy of the gas is equal to the heat in plus minus the work done on the gas or by the gas, we have that the work is actually equal to the heat added into the system. And because the gas expanded, the work done on the gas is negative, and they tell you how much heat is added, 500 joules between K and L, so that's negative 500 joules. For the next part they say find the work done on the gas during L to M process or adiabatic expansion. So in adiabatic expansion you have the change of heat added into the system is equal to 0. Then you have delta U, the internal energy of the gas, is equal to 0 plus the work done on the gas. So your work is equal to the change of internal energy, which is 3/2 nR and delta T. So that gives me 3/2, and I calculated that the moles in the gas is 0.24, and R is 8.3, and the change of the temperature, it goes 300 right here, 300 Kelvin, and 200 Kelvin. So the change of the temperature is 100. So from here I can calculate the work is equal to also a negative number, so I should have plugged in right here negative 100 because it's the final minus initial. 200 minus 300, so it's going to be negative 299 joules. So we had KL process, K to L, and now we have LM. So it's still expansion, so we still have negative work. In D, they ask how much heat is expelled between M and N. It's another isothermal process. So to calculate how much heat is expelled, that is heat to the cold reservoir. And I can use, so this one is going to be from M to N process. And I can use the efficiency to do these calculations. I can say the efficiency is equal to 1 minus T cold over T hot, and equals to 1 over Q cold over Q hot. And from here I can say that T cold over T hot is equal to Q cold over Q hot. And if I plug in my numbers, I have T cold 200 divided by T hot 300, and for heat I have the cold reservoir I'm looking for, and the hot reservoir in the engine is 500 is given in the problem. So I get that the heat that is expelled during M process between M and N is 333 joules. And for the last part, they ask me to find the change in internal energy in the process between N and K. So between N and K, it's another adiabatic process where the temperature changes, but heat stays the same. So between N and K, it's adiabatic process. Again, Q is equal to 0. And from the first law of thermodynamics, I have delta U is equal to Q plus minus the work done on the system. And that gives me delta U is equal to 0 plus minus the work. So if I'm calculating the change of internal energy, which is the same as work, so change of internal energy is equal to 3/2 and R and delta T. So I have 3/2 and is 0.24, R is 8.3, and the temperature changes final is 300, so it goes from N to K, so it goes from 200 to 300. So I have 100 is the change of the temperature. In this case it is positive, so delta U is equal to 299 joules. I think most of these questions, they are there's a lot of stuff going on in every single one PV diagram problem, but I don't think they are very complicated. You just have to know which formula to use and how, and for that you need practice. So we're gonna do more questions where you can see me solving questions and explaining where things are coming from, and so if you see something like this yourself, you will know how to do it just because you've seen so many practice questions. So let's look at the next question. So here is the next question, and they say the heat engine contains an ideal monatomic gas confined to a cylinder by a movable piston. The gas starts at A. The temperature at A is 300 Kelvin. So I'm just going to write down everything that I know here. 300 Kelvin. And goes from B to C is isothermal. So B to C is isothermal. and then find the number of moles of gas at the temperature and the temperature at B. So I'm gonna have my A in purple, and I have PA, VA is equal to nRTA. From here I can calculate that N is equal to 0.2 mole, because the pressure is 1 atmospheric at A, and the volume is 5 liters, that is 510 to the negative 3 meter cubic. R is the gas constant, which is 8.3, and the temperature they give you 300, so I can calculate what N is equal to. Then I can use the same trick, or the ideal gas equation, where I can have PA VA divided by TA is equal to PB VB divided by TB. And from here I'm going to calculate that TB is equal to 900 Kelvin, because PB is 310 to the 5th, 3 atmospheric. The volume at B did not change, it's still the same, 510 to the negative 3 meter cubic. And the temperature at B we're asked to find. So now, because I know that between B and C it's isothermal process, I know that through the whole BC it's gonna stay at 900 Kelvin. So the temperature at C is still 900 Kelvin. So I have 900 Kelvin at B, and I have 900 Kelvin at C. For B, they ask you to find the change of internal energy, heat, and work done for the isovolumetric process between A and B. So for B part, it's an isovolumetric process, so the work is equal to 0 because the volume stayed the same. And I know that from the first law of thermodynamics, delta U is equal to Q plus minus the work done on the gas or by the gas. And from here, I have that delta U is equal to the Q, and that is the halves nR delta T. So my delta U and Q are the same numbers, so I found the work. And delta U and Q. So here I plug in the numbers, and I found that the internal energy and the heat added to the system equal to each other and equal to 1494 joules. For C, they ask you to repeat for the isothermal process between B and C. So they want you to calculate the work done, the internal energy, and the heat between B and C. So the C, I have the internal energy again is equal to the heat added into the system and the work done on the gas or by the gas. And then I have the internal energy, because it's isothermal process, delta U is equal to 0. So you have Q is equal to the work, and the work is equal to the formula for isothermal, the one that I don't require you to remember, just know how to use it. So it's nRT and natural log, and then I have V C over VB, the final over initial. So if I plug in my numbers, I will get that Q is equal to W and equals to negative, the temperature stays 900 for isothermal between B and C. So I have the work is equal to negative 1641 joules. And it's negative again because there is expansion between B and C, the gas is expanding, the volume final is larger than initial, so the work done by the gas, not on the gas. For D, they ask you to do the same and continue calculating the work done and the energy for the process between C and A. So again, I have delta U is equal to Q plus minus the work done on the gas, and delta U is 3/2 and R delta T, and the temperature changes between C and A. So at C it's still 900 and A is 300. So we have that part for delta U, and then we have equals to Q, heat added into the system, and plus the work, but the work is the area underneath the graph, and the work is positive in this case. So I will have plus, and so I'm just gonna say area. And now if I plug in all my numbers, I have 3/2 and R delta T. So T goes from 900 to 300, so it's final minus initial, it's negative 600. So 3/2 and RT will give me negative 1494 joules of energy. And then I have Q, and then if I do the area underneath the graph, I'm gonna get the width is 10 to the negative 3, and the height is 1 10 to the 5th. So that will give me 1000. And then from here I see that the heat added into the system is equal to, or taken away from the system, 2494. So it's negative 2494 joules, and the number is negative. I ran out of space at the bottom, so for E, they ask you find the net change in the internal energy for the complete cycle. So for E, the complete cycle, so I'm gonna do calculations on the top. So for E part, the energy for the complete cycle, or the change of energy in the complete cycle, is over 0, since the internal and final states are the same. So the gas comes back to the initial state, where it means the gas internal energy at the end is this, there's no change of energy at the end. So the change of energy through the whole cycle is equal to 0 joules. And for the last part, they ask you to find the thermal energy Q high transferred into the system, the thermal energy rejected Q cold, or spilled Q cold, the thermal efficiency and network on the environment performed by the engine. So I'm gonna write for this is our F, and efficiency is equal to the work done by the gas on the environment, the positive work on the environment, over the heat that comes into the system. So the work done on the environment is only happening one time, and it is in between B and C. So the one that we did between B and C is in yellow. So that work was the only done on the environment. So this is the one. So that is negative 1641. So that was positive work on the environment, 1641. I don't plug in my negative. But also the work done on the gas was negative on the environment, but positive on the gas, and that's the work where we had 1000. So it's the area and that was the work done on the gas, positive, but for the environment it was negative, so that's negative 1000. And so that's the net work done on the gas by the environment, or on the system, on the environment by the gas. And then the heat added into the system. So we have heat added into the system twice. One time it is added in B. So in B we had the Q was 1494. So that was the heat added into the system, so 1494. And then one more time the heat was taken out of the system, and that was in C. So that is again our BC process. So in this case we had the heat taken out of the system, which was 1641, so that goes in the denominator, 1641 for the heat, 1641, and I'm gonna add this because that's all the energy, all the heat energy that was used in the system during this process. So that will give me 641 divided by 3135. And from here I see that the efficiency is equal to 20.45%. So to answer E correctly, we have the thermal energy transferred into the system and ejected by the system is 35, so the sum of all heat is 3135 joules. The net work done on the environment performed by the engine, so the net work is equal to 641 joules, and the efficiency is 20.45. So this is your net work, this is your heat, and then you have the efficiency. Another very complicated question to solve, but I hope it makes sense to see the explanation as we are solving. So here's another question that I think you should try to solve on your own. So go ahead and pause it, and I'm gonna show you the work and talk to you a little bit through the process, but I want you to try to solve this question on your own. So here are my calculations, and I have to find the heat change of energy and the work for A. So because between A and B it is as isovolumetric process, so the work in between A and B is equal to 0, and the change of internal energy is equal to the heat, which is 3/2 nRT, and the temperature changes between A 300 to B 600. So if I plug in all my numbers, I get the change of energy is equal to 151, and that is actually the heat added into the system as well. So for the next one, I had to find for isothermal process the work, and because for isothermal process I have the internal energy, the temperature doesn't change, the internal energy of the gas does not change, so that one is equal to 0. So in this case my work on VC is actually equal to the heat added into the system. So I did the formula for isothermal process, where it's the volume final over initial. So I have isothermal process formula, and I plugged it in, and I found what the work is equal to, and that is actually the heat as well. So that is equal to the heat between B and C. For C, I repeated the process between C and A. So between C and A, I can calculate the area with the area underneath the graph, which is the work. So I did the calculations of the work underneath the graph, so that gives me 100 joules. and the internal energy I can use 3/2 nRT, which is 151, because at A the temperature is 300 and at C the temperature is 600, so it's 3/2 nR delta T. And I calculated the heat in the between C and A, added or taken away out of the system. And then for the next part, I had to calculate the efficiency and cold and hot reservoir and efficiency. So for the cold reservoir, I have 251. For the hot reservoir, I have 291. So the heat for 251, it is in right here. This is where we spill the energy between C and A. And for the heat for 291, that's the work and the heat in B and A and B. So that is coming from A and B. I have the heat in B is 141, but the work is negative, but the heat is positive. And then and in A I have 151. So 151 and 140 will give me 291. So the and the net work is equal to, so in BC I have the work on the environment is 140, and it is in CA I have the work on the gas is negative 100. So the net work is 40. And now if I use the efficiency formula, I get that I can use either formula. So I could get it from here, the efficiency, or I could do it from here. I chose this part. And I get the efficiency of the engine is 13.75. And then for the last question, they ask you what find the work of the engine. So that would be for part D or E. That would be E. So that would be E. So another somewhat complicated question. Haven't seen anything like this complicated on AP exam, but parts of this question may appear on AP exam. Many of the questions that I solved today, also you can find them in our notes that I posted for you online. So every single question is solved and you can see the work done in those notes as well. If something is confusing, maybe you can look at the notes as well. I know that these questions look very complicated. They're not as difficult as they seem if you spend time on them, but because there's so many different details and you have to think about whether the heat was added to the system, taken away from the system, why the gas is expanding. So you have to spend time processing all this information. But I will finish this video on laws of thermodynamics 4 now, and the 5 is gonna have entropy. So the video 5 is gonna have entropy and more practice with the PV diagrams. So thank you for watching this video, and I will see you in the next one.